Polymers are tough. Polymers are strong. They're as hard as nails and soft and cuddly. They bounce. They glue. They play music. They take you into outer space. You wear them as clothes. You walk around on them. You drive on them. You paint with them. You control electricity with them, mould them into all sorts of things. And if you wear contacts or glasses with plastic lenses, then you see your whole world through them. Getting the picture? Polymers are everywhere. In fact, life itself is made of polymers. Most of this is the polymer cellulose, growing in the form of wood. Most of flesh and blood are protein polymers, as is skin and fur, nails and claws. That's right, we ourselves are part of nature's polymer creations. So, what is a polymer?
The word polymer comes from the Greek words poly, meaning many, and meros, meaning parts. Polymers are huge molecules that have many repeating parts. For example, one of the latest creations is ultra-high molecular weight polyethylene, as used in bulletproof vests. That's the ethene molecule joined again and again and again in chains of up to 500,000 units long, making it super strong. How do we do it? We use the amazing combining power of the carbon atom.
Carbon sits in a special position on the periodic table. It has 4 outer electrons, exactly half the number required to create a very stable outer shell of 8, like neon, and 4 up from the smaller and equally stable arrangement of helium. So carbon is delicately balanced in the middle, halfway between wanting to lose electrons and wanting to gain electrons. This uncertainty makes carbon the most subtle atom of all.
Carbon's electron structure makes it incredibly versatile. It can join endlessly to itself in chains, sheets, or even blocks. Here's a model of diamond, and even this model, which has soft plastic links, goes quite rigid in this arrangement. Diamond is the hardest substance known. These are covalent bonds where every carbon atom is sharing one of its outer electrons with a neighbour. So each of these bonds represents a shared pair, making 2, 4, 6, 8. So every carbon gets a perfect 8. These strong bonds lock every atom into an exact position in a huge macromolecule. Diamond is the extreme case of how carbon can combine perfectly with itself.
Beautiful as a diamond might be, it's not considered to be an organic substance because it doesn't come from life. Yet life's compounds also depend on this magnificent ability of carbon. All organic substances are examples of carbon connecting not only with itself but also with other elements. Carbon is the binder for many kinds of giant molecules. Take cellulose. Most plant fibres are made of cellulose. In 1819, a French chemist, Henri Brassenot, boiled up sawdust, linen and bark, and he got glucose. Glucose is a simple sugar. Russian chemist Gottlieb Kirchhoff boiled up starch, and he also got glucose. It was easy to guess that starch and cellulose was somehow made of glucose. Others worked out glucose formula as C6H12O6, which immediately suggested a combination of 6 molecules of water with 6 carbon atoms. So glucose and all other sugars were put into a class called carbohydrates. Starch and cellulose turned out to be glucose molecules strung together in long chains.
Yet everyone knows you can eat potatoes, but you can't eat wood. In other words, you can digest starch, but you can't digest cellulose. Why? Remember in the last program how I showed that if you have 4 different groups around a carbon atom, there are 2 and only 2 ways you can represent them? Well, here's glucose, and it comes in 2 forms. If the OH group on the first carbon points down, it's alpha glucose, and if it points up, it's beta glucose. In every other way, the molecule is identical. A chain of alpha glucoses makes starch, and a chain of beta glucoses makes cellulose. Unfortunately, we humans just don't have the enzyme needed to break down a beta-linked glucose chain. We can't digest cellulose.
But if there's one polymer that's everywhere, it's cellulose. In wood, straw, cotton, hemp, and flax. We've used cellulose for thousands of years, and it would be cellulose that would launch chemists into the world of synthetic polymers.
In the early 19th century, the word polymer was in use. So chemists knew that polymers were compounds made of smaller units that they called monomers or single parts. But they didn't know the detail, and in fact, several breakthroughs were made by sheer accident. For example, in 1839, Charles Goodyear spilled a mixture of rubber and sulphur on a hot stove, and when he scraped it off, he found that the rubber remained springy, not gooey. He had discovered how to vulcanise rubber. In 1846, a Swiss chemist was experimenting in his kitchen when he discovered a dramatic quality of cellulose.
Christian Schoenbein's accident was to spill a mixture of sulfuric and nitric acid on the floor. In his haste to mop it up, he grabbed his wife's cotton apron. But as it soaked up the acid, he didn't realise a chemical reaction was happening with the cellulose of the apron. The nitric acid made cellulose nitrate. And when he finally hung the apron over the stove to dry, smoky old-fashioned gunpowder was finished. Cellulose nitrate would start a revolution in explosives. It would lead to nitroglycerin, TNT and cyclonite. These chemicals still power the weapons of the world, are still a major force in engineering.
So cellulose nitrate was the first explosive polymer, but it didn't end there. It's explosive when all of the OH units on the glucose molecule are replaced by nitrate groups. But what if they're not all replaced? Would that make it less explosive? The answer is not only yes, but it led to a brand new material, celluloid.
The reason for celluloid was elephants, or more accurately, the lack of them. Ivory was being used in everything from piano keys to billiard balls, and it was becoming harder to get. In 1863, a billiard ball company offered $10,000 to anyone who would come up with a substitute for ivory.
The prize attracted inventor John Wesley Hyatt. He took partly nitrated cellulose and dissolved it with camphor into a mixture of alcohol and ether. When they evaporated, they left a substance that was hard at room temperature but soft when you heated it. It was the very first thermoplastic. Hyatt's billiard balls weren't a raging success because they tended to spark a bit when they hit hard, but the stuff was great for lots of other things. He called it celluloid because it was based on cellulose.
In the last half of the 19th century, celluloid was being used for everything from ping pong balls and dental plates to the new sensation photographic film. But unfortunately, celluloid still had an urge to burn.
Ping pong balls are still made from celluloid, and if I hold one in a flame, you can see the problem. Because it is a form of cellulose nitrate, it burns very quickly. A better way to go would be to replace the nitrate groups with more stable ones. Film was once made from cellulose nitrate, but exactly this problem led them to change it to cellulose acetate, which was then called safety film because it won't burn. Most film today is still cellulose acetate film, but a lot of it now is made from an even more modern polymer, polyester. This stuff is not a modified natural polymer, it's completely synthetic.
The first synthetic polymer arrives in 1909 when Leo Baekeland develops Bakelite, a three-dimensional polymer. Bakelite forms when a mixture of phenol and formaldehyde polymerises. A molecule of formaldehyde comes in between two molecules of phenol, joining the two aromatic rings with a methylene group, that's a CH2 group, and forming a molecule of water. So the rings are now bound in 3 dimensions, and you get a web that is so strong that it won't melt before it burns. It's classed as a thermoset plastic.
But Bakelite, seen here formed into a gramophone record, was to be the last important polymer of the classical chemists. By the 1920s, hit and miss chemistry was out and electron bonding theory was in.
For the first time, chemists had a clear idea of the actual macromolecular structure of polymers. This began the modern era of polymers, and the first big one, in the early 1930s, was nylon.
Like Bakelite, nylon is a condensation polymer. This means that when two reagent molecules come together, their functional groups react to form a small molecule, usually water, that comes off and a new bond is formed. Here you can see the reagents for nylon 610. One of the reagents is dissolved in water, and now, floating above it, the other is dissolved in hexane. Nylon is forming at the interface of these two layers, and I can draw up a thread like this. Nylon is unlike Bakelite, however, in that, like celluloid, it will melt with heat and reharden at room temperature. It's a thermoplastic.
All polymers are classed as either thermoplastics, which can be heated and remoulded, or thermoset plastics, which once formed are not softened by heat. The difference is due to the degree of cross-linking between the macromolecular chains. Strong cross-links impart a rigid crystalline quality, which resists heat. Weaker cross-links can make an elastomer. The material deforms but springs right back. Polymers all have a glass transition temperature, below which they go hard and brittle. Some, like polystyrene, have a glass transition temperature above room temperature and are used as hard plastic. Others, like polyethylene, have a low glass transition temperature and they are soft and pliable. Today, however, we rely less on natural polymers. Nowadays, a great deal of the raw material for organic synthesis is supplied by the petrochemical industry. And that's another side to polymers which is tied to an even bigger story of coal and